HNMR stands for Proton Nuclear Magnetic Resonance. Taking advantage of radio waves, HNMR spectra produce chemical shifts with peaks that indicate the environments hydrogen atoms are in this molecule, as well as how many hydrogens are in each environment. How exactly does this technology work? Let's first take a look at the theory, then analyze some samples as practice. Each hydrogen nucleus or proton has one of two spin states. It is either in the low-energy alpha state or in the high-energy beta state. The spinning, positively charged nucleus forms a tiny magnet, which can be denoted by a vector. Which spin state it is in gives us a hint of how the hydrogen would be influenced by a magnetic field. If the nucleus is in the alpha state, then when there is an external magnetic field, or B0, it will orient itself in the same direction as the magnetic field. If the nucleus is in the beta state, then when there is an external magnetic field, it will orient itself in the opposite direction as the magnetic field. Actually, other nuclei with an odd number of protons or neutrons, such as carbon nuclei, behave like a tiny magnet too, as long as they have a non-zero spin. So besides H1 NMR, there are C13 NMR and 15 NMR, etc. The interesting thing is that when excess energy is applied to the alpha hydrogen nucleus in the magnetic field, it can change into a beta state nucleus. Originally, it aligns with the orientation of the magnetic field, but after absorbing energy, it turns 180 degrees to the opposite direction. When this happens, we say that the nucleus is now in resonance with the magnetic field. The amount of energy required for the transition can be calculated by Planck's equation, delta E equals h mu. In experiments, we often measure the amount of energy emitted when the proton comes down from the high-energy beta state back to the low-energy alpha state. And we have found that the energy lies in the radio wave region. If we look at the electromagnetic spectrum, it has the longest wavelength, lowest frequency, and least energy. That said, the delta E value is different for protons in various chemical environments. The more electrons that surround the proton, the higher the shielding effect. Such protons are less affected by the magnetic field than de-shielded protons, so they need lower energy or lower frequency to achieve resonance. The frequency a proton absorbs to achieve resonance can be measured with HNMR equipment and converted through a formula into a chemical shift value. The higher the frequency, the larger the shift. This chemical shift data is then presented on an HNMR spectrum. To learn how to obtain the HNMR spectrum, we now enter the lab for practice. We have ethanol, ethanol, ethanoic acid, and an unknown substance. These are our 4 samples. The first step is to prepare a sample. The standard procedure is to add 0.6 milliliters of the substance to be analyzed before dissolving it in a special chloroform solvent, which contains TMS as well as deuterated chloroform. Now remember TMS because we're going to come back to it later in this video. The second step is to put the sample inside the equipment. Use the sample holder to check whether we have enough solution. In the upcoming experiment, electromagnetic waves will hit the black boxes to make the spin state transitions that we mentioned before. So only when there is fluid above the horizontal line are we ready to proceed. Now place the sample test tube inside the slot at the top of the equipment, then let it drop in. Now we program orders using the computer. There are 4 small steps. Number 1. Set the parameters for HNMR. Number 2. Lock the magnetic field. Choose the solvent we just used. In this case, click on CdCl3. Number 3. Do gradient shimming to further stabilize the magnetic field. The higher the line, the more even the magnetic field is, the more standardized and comparable the chemical shifts are, the more reliable the H&MR results. Number 4. Set the resonance frequency of the equipment to be the appropriate value for H&MR. These done, we can start to collect data. On the screen, we obtain what's called FID signals, but don't worry if you can't interpret them because the Fourier transform will quickly resolve the NMR spectrum we are familiar with. Our final step is to analyze the spectrum. The x-axis represents chemical shift. The unit is parts per million, ppm. The y-axis, on the other hand, indicates intensity. Every time you obtain a spectrum, we pay attention to 5 of its features. Number 1. TMS signal. Do you remember TMS? It was in our solvent. On the far right of the spectrum, the small signal belongs to TMS. Whenever we run H&MR, whatever substance we analyze, we would produce a chemical shift using tetramethylsilane, SiCH3,4. It is used as a standard reference. This chemical shift is said to be 0 and is deducted from all other chemical shifts produced in the experiment. If you wonder why, it is because all 12 hydrogen atoms in TMS are in the same methyl environment, one that is highly shielded. This gives TMS an extremely low shift. Number 2. The number of chemical shift peaks. Ceteris paribus, a specific chemical environment requires radio wave of a specific frequency to change the spin state of its protons. Therefore, each chemical environment has a corresponding chemical shift. The number of chemical environments in the compound can be deduced from the number of chemical shift peaks. Thus, we can say that this sample has 3 environments. Number 3. Integration traces. The integration traces of peaks are the areas under every peak integrated into lines of different heights. Since the protons in the same environment all share the same specific shift, the height ratio of the integration traces shows the relative numbers of hydrogen atoms in different chemical environments. This sample has the ratio 3 to 2 to 1. Number 4. Values of chemical shift. A chemical shift is an H&MR signal position relative to the TMS signal. According to the principle of H&MR, its value indicates the specific type of chemical environment that is present. Here, there is a methyl peak around 1.0 parts per million. The peak near 3.5 ppm is for CH2, and the peak near 3.0 ppm is for hydroxyl. The data booklet can confirm our guesses, therefore this molecule is ethanol. Number 5. Split peaks. The above 4 features can be observed from a low-resolution NMR spectrum. But if we get a high-resolution spectrum, we can extract more information from the split peaks, which are the jagged lines around each chemical shift peak and the raw materials for calculating an integration trace. Let's first take a look at this hypothetical high-resolution NMR spectrum of ethanol. It's a simpler example than ethanol. We have mentioned that each proton has 2 possible spin states. So if we zoom in to the methyl protons, we can predict something called spin-spin coupling. For 50% of the time, methyl's neighboring carbon is bonded to or coupled with a hydrogen at alpha state, and for the rest 50%, methyl's neighboring carbon is bonded to a hydrogen at beta state. Beta state hydrogen is more shielding than alpha state hydrogen, so methyl's chemical shift will be slightly lower when it is coupled with aldehyde with hydrogen at beta state. 2 close yet separate lines make up the doublet of a split peak. The relative intensities of these 2 lines are 1 to 1, according to Pascal's triangle. Now suppose that 2 protons are on the neighboring carbon for a change. This is the case of ethanol's methyl group. The 2 hydrogens on CH2 can be alpha-alpha, alpha-beta, beta-alpha, or beta-beta. The three valid combinations are thus at a ratio of 1 to 2 to 1. A triplet with these relative intensities would be produced, so on and so forth. Over time, we summarize two handy rules for analyzing a high-resolution NMR spectrum. First, there are n+1 split peaks where the neighboring carbon has n hydrogen nuclei directly bonded to it. Secondly, the relative intensities of these split peaks are the nth row in Pascal's triangle. Check the principle on the CH2 group. It is bonded to methyl, and we do see 3 plus 1 equals 4 peaks with a height ratio 1 to 3 to 3 to 1. Repeat the lab process with another sample. The second spectrum shows 2 peaks of the height ratio 3 to 1. There are no split peaks, so the molecule cannot be ethanol. Split peaks only occur if hydrogens are directly bonded to the neighboring carbon. The carboxyl hydrogen is directly bonded to oxygen instead of carbon. Indeed, ethanoic acid satisfies all requirements. We then infer that the peak around 2.0 parts per million is for methyl, and the peak around 11 ppm is for carboxyl. The lower shift peak results from methyl, which is a more shielded chemical environment. This fits with H&MR theory, because take a look at the two hydrogen environments in ethanoic acid. You can find that the highly electronegative oxygen atom pulls electrons away from the proton in the carboxyl group, making it more de-shielded. The lower electronactivity of carbon makes methyl protons more shielded on the other hand. Without electrons to block out fields in the vicinity, the de-shielded carboxyl proton will need energy with higher frequency to achieve resonance compared with the methyl protons. In other words, E2 is smaller than E1. That's why de-shielded environments have higher chemical shifts and vice versa.